Okay, so let's take a look at problem 5 here with the rock thrown from the top of a tall building at an angle blah de blah above the horizontal, and a couple things we want to know. So let's see, what do we have here? We have the horizontal range is equal to the height of the building, and we want to know what speed the rock was thrown at. We want to know how long it's in the air. So if we're not clear what to do yet, the thing to do, oh my gosh, that's huge. Let's see. Sorry, just trying to get my little paint program working. All right, so what we want to do here is let's draw a little diagram. Here's our, okay, that'll work. So there's our building and the ground. You don't really have to cross-hatch it in, but I'm just doing that. And so we have this rock that's thrown from the top of it, right? And it's launched at some initial velocity, which is unknown. That's what we have to find. And at an angle that I'm having trouble drawing here, theta, okay, which is given. And then it goes through this sort of split, okay, something like that. Probably less ugly than that, but there you go. So let's see, what do we have here? Let me draw over here and say the height that it's launched from, we're going to call that h. And so we want to find, let's see, what are we told? We're told that the distance it travels horizontally, the horizontal range, is the same as the height. So we're going to call that h2, h as well, not h number 2. And then we also know that, well, that's what we know. And we want to find the total time of flight. So I'm going to let t, I'm going to try that again, t equals time of flight. This is the first video I've done this year, so I apologize if this looks strange. I haven't quite gotten all the settings the way I want them. So anyway, let's go here now and actually, I mean, the first thing to do, right, is figure out what you know, how this h and this h are going to relate to, well, how the distance here is going to relate to the angle, the initial velocity. Of course, we have gravity going downwards, so let me just plot out and get an x and y axis, and gravity is going like that. That's the acceleration here. So the x component of that is 0. The y component is negative g. Remember that because g itself is a positive number. So if it's going to go in the negative y direction, if the acceleration is going to go in negative y, then the acceleration has to be negative g. Okay, so then I'm going to sort of divide this up, and we're going to have an x side and a y side, and do that. Okay, so going from here to here, right, this is the only thing we have, or the only stretch we have. So I'm going to call this just, you know, state 1 to state 2. Okay, so 1, 2, you do something like that. This is more writing than you would have to do. So let's say on the y side, we know that its displacement is going to be negative h. Okay, so delta y is negative h. Initial y velocity, we're going to break this down into components, right? So there's your v naught, theta. Wow, that's the worst theta ever. Okay, that's a somewhat better theta. Okay, so vx naught is going to be like that. Vy naught, we're measuring from horizontal, so that means Vx naught is going to be equal to V naught cosine theta, and of course Vy naught is equal to V naught sine theta. Okay, so Vy, I guess I should say it's state 1, but you know, whatever. How you do notation is up to you, and don't slave yourself to me because I'm horrible at it. Y acceleration then is negative g, and of course the time that passes, which is the only thing that can go between these two, you know, the x side and the y side. I'm going to say delta t is equal to this t time of flight we had. So, you know, there you go. On the x side, the x displacement is positive h, right? And then the initial x velocity is going to be v naught, and of course, look here, I used a 0, v naught for initial velocity, and here I'm saying 1 is state 1, and I'm doing, this is horrible. This is horrible, horrible notation. Well, not, I mean, okay, so it's horrible, but on the other hand, it doesn't care. It doesn't matter, you know? So vx1 is that. Since ax is 0, right, then Vx is actually constant. So I could just say, you know, Vx constant here, okay? And so then to relate, and then of course the delta t applies to both sides, okay? I'm doing way more drawing than I need to, just to recap. So I'm going to then just plug in a constant horizontal velocity equation, right? Whatever horizontal velocity it has at the start, it's going to keep all the way across. So, you know, delta x equals Vx times delta t, okay, if you have constant horizontal velocity. Or if you want to take one step back, you could apply the full, what is this, cake 2, and say, okay, it's Vx1 times delta t plus 1/2 y acceleration delta t squared, or sorry, x acceleration, excuse me, plus 1/2 x acceleration delta t squared, and then x acceleration is 0, so that goes away. So what that's going to give us here, and I'm just going to take this over here because I don't have room down here, is that your delta x, which is h, is going to be this Vx, which is V naught cosine theta, times t. So V naught cosine theta times t. Okay, so that's the equation we get out of x. I'm going to sort of, you know, dash dot that. And then here we've got, we can apply some cake equation. We've got time, we've got displacement. If we have time and displacement and we want to use them both, then really the thing to do is do cake 2. So cake 2, formally speaking, says, you know, delta y equals Vy initial delta t plus 1/2 y acceleration delta t whole quantity squared. And then we're going to get, you know, negative h, let me move this down a little, negative h equals V naught sine theta, and then I'm going to plug in, you know, t for delta t, because I said I could here, okay. And then ay is negative g, so I'm going to go minus 1/2 g t squared, and this then gets you that. So these two equations now, what do we have here? Let me, colors. Oh no, not those colors. Colors, yay, okay. You can't see, but okay, so I'm going to mark in blue, I'm going to mark the givens. The givens are h, theta, okay, and of course g. So t now is a mystery, and that's part B, I think we have to solve, and V naught is a mystery, that's part A. So these are two equations with two unknowns, which means you just apply your standard simultaneous equations tricks. If you look at this, you might say, zoinks, look, you know, this is quadratic. This is me quadratic in t. And there might, you know, you might have to go through a quadratic to do this if you do it some ways, and that's fine. You can solve it with a quadratic. But what I find is the easier way to solve it is, I'm going to do now my solution in, let's go with, ooh, purple. Purple's fun. So I'm just going to take these two equations up here. And what I'm going to do is I'm going to take this h here and plug it in there. Okay? So what I'm going to get now is negative, and this equation, but I'm plugging in the h. So negative V naught cosine theta times t, okay, equals V naught sine theta times t minus 1/2 g t squared. So then, of course, we solve this now. We want to gather up on the left-hand side all the single t terms, okay? So we're going to go negative V naught times, and I'm going to go ahead and gather the t's out. And then you're going to get the cosine theta that was here before, and then you subtract over the term with sine theta. So sine theta, so like that, right? Equals negative 1/2 g t squared. Okay, now let's zoink out the t, take care of the negative. And what we can get here now is we can solve now for, I guess, either solve for V naught or for t, sort of our choice. So we can go, fine, let's just solve for t. We can get t equals, and this is going to be 2 V naught over g times, and this might get tricky, cosine theta plus sine theta. Okay, and of course this looks ugly, but remember, you're given theta, so it's really just plug and chug here. You get a number here, and you got it, right? And then, so we can plug it into one of these to actually find what V naught is. I would say let's plug into the second one, just because that's simpler, right? So taking this down there, and then going like that, And I'll switch colors now because I just feel like switching colors, and go to, ooh, red. How about red? Okay, so let's do red now. And then we'll get now, so I'm just going to take the first this equation here and plug in the t. Okay, so h equals v naught cosine theta times t, which is then 2 v naught over g times this ugly cos theta plus sine theta. Okay, and oh, look, ugly, ugly, ugly. Well, yes, it is. Okay, so let's see, what do we want to solve for? Let me back up and before I start doing stuff, figure out what I want to solve for. We want to solve for v naught, right? So what I'm going to do is take, well, okay, so what I'm going to do is go h equals 2 over g. So I'm going to keep my 2 over g. I'm pulling my v naughts out, and I'm going to put them at the end so it's easier to, figure out what the hell I'm doing. It's not usually easy to figure out what I'm doing. Let me tell you that. So sine theta, and then we have our v naught squared because we have the 2 v naughts on this side. So then the final answer then gives us v naught equals, bleh, let's look, it's going to be, so the 2 is going to come over 1/2 g h, and then actually this should be 1 over cosine theta times cos theta plus sine theta. Of course, this does look ugly. Absolutely looks ugly. But plug in, when you know theta, you're given theta, right? So you just plug that in here. And then you're given h, plug that in. You know g, plug that in. Obviously you know 1/2. So that solves you for v naught. And then you can just take, whatever equation you want, I guess this one or whatever, and then solve for t. And I'll leave finding the final velocity to you that's part C. But that shouldn't be very hard at this point. So there you go. That's how you do that particular sort of thorny problem. If I have time, I might go on to the next problem on this particular web assignment, which is the weird range thing. So there you go.